So, in the past sections, we've studied we've studied linear equations with three or more variables, and we've also looked at systems of linear inequalities. So, with these tools, we can now begin what's called linear programming, and basically, we're gonna have like we're gonna have like a problem, and there's going to be like restraints within the problem, and we're gonna write those restraints as inequalities and then use those inequalities to find a feasible region which will be like most economically efficient for the company. So for the example problem, we have a school board is investigating various ways of composing faculty for a proposed new elementary school. They can hire teachers and aides. The amount of money the school district will have to spend on salaries each year depends on how many teachers and aides are hired. So we're going to let T be the number of teachers, A be the number of aides hired, and D be the number of thousands of dollars spent on salaries. So so we have this new school, that's the problem, and then we have all these restraints about the faculty members, and basically we're going to want to see what is going to have a minimum cost for this school. It's going to depend on how many teachers and aides are hired, but we have all these restraints, so we're going to graph these restraints as inequalities, then look at the region that overlaps to figure out which is going to have the minimum cost. So the restraint says that the board finds that the average teacher's annual salary is 15,000 and the average is 10,000. So it's not really a restraint, but we can write an equation for that relationship. So for that first restraint I, we're going to say that the number of dollars spent D is going to equal 15T plus 10A. Because the reason we say that is because D is the number of thousands of dollars spent, and so the average teacher's salary is $15,000 and the average aides is $10,000. The second restraint says that the building can accommodate no more than 50 faculty members total. So that means that to write a relationship, to write an inequality with that, the number of teachers plus the number of aides has to be less than or equal to 50. For the third restraint, it says that the minimum of 20 faculty members is needed to staff the school. So that means that the faculty members, which is the number of teachers plus the number of aides, has to be greater than or equal to 20. The fourth restraint says that there must be at least 12 teachers. So that means that just T has to be greater than or equal to 12. The fifth restraint says the number of teachers must be at least the number of half the aides. Or half the number of aides. So that means that the number of teachers has to be greater than or equal to 1/2 of the aides. And the final restraint says that it is impossible to hire a negative number of teachers or aides. So that's kind of obvious, but basically that means that T must be greater than or equal to 0, and aides must be greater than or equal to 0. So the sixth inequality, or to the right, actually form a system of inequalities, and this system can be plotted using the techniques of last section. So that's what I did here, and I went and plotted all these inequalities, and basically the overlapping region between all of them ends up being right here in the shaded portion. So ordered pairs in this region are possible or feasible. So for this reason, we're going to call this region the feasible region. So at this point, we can now use the equation D equals 15T plus 10A to find out which of these ordered pairs is going to give a minimum cost. So since D, like I have this set up as this is the A axes, the aides, and this is the T axes for the teachers. But since D is a third variable, the D axis should be coming up vertically out of the page. However, there is a clever way of reducing this three-dimensional problem to a two-dimensional one. So let's say we want to find the portion of the region in which the cost is less than uh, some fixed amount, or let's say like just $600,000. So what that would mean is we'd have 15t plus 10a is less than or equal to 600. So now, solving for a in terms of t, we have 10a is less than or equal to negative 15t plus 600, or a is less than or equal to negative 3 halves t plus 60. So now this inequality, we can graph it on the feasible region. So I went ahead and just graphed only the feasible region, and on top of that I graphed the inequality that makes the cost less than or equal to 600,000, which was this inequality right here. So as you can see, the values of t and a that make the cost less than or equal to 600,000 are going to be right here. So this now eliminates like this intersection point and this one. So now we can pick another cost value that we want to say we can find the number of teachers and aides that will make the cost less than. So let's say we pick 400,000, then 15t plus 10a would have to be less than or equal to 400 because it's 400,000. Then solving for a, we're going to do it the same way and find that 10a is going to be less than or equal to negative 15t plus 400. And then that a is less than or equal to negative 3 halves t plus 40. So you may notice that this new inequality has the same slope as this one, but just a different y-intercept. So the portion of the feasible region that's going to be less than or equal to that is going to be the ordered pairs that are under this line. So drawing this graph in, it's going to intersect at 40, and let's see, the slope has it just has a slope of negative 3 halves, so about here. So this is going to be, you can see that the line is parallel to this one because they have the same slope. And so now you can see that the ordered pair that's going to have the minimum cost is going to be right here. Whoops. So this ordered pair, we're going to have the minimum cost. So now that we know that the minimum cost occurs at this intersection, we need to find that particular intersection between these two equations. So those two equations where it intersects happen to be t equals 12, because it's the vertical line at t equals 12, and that t plus a had to be greater than t plus a basically equals 20. It was greater than or equals 20, but we're solving the intersection point now, so we can set it up like this. Now we can solve these two linear equations by just making the substitution for 12 for t. So we can say 12 plus a equals 20, and then a equals 8. So now we know that the minimum cost occurs at the ordered pair of t equals 12, a equals 8. So now we know the minimum cost occurs at this point, but we need to find that actual cost. But we can just substitute this point into the equation that we have, and that is d equals 15t plus 10a. So then, making the substitution, we'll say d equals 15 times 12 plus 10 times 8, or d equals 260. So that means that the minimum cost that could be achieved with these restraints is $260,000. Now, if we wanted to find the maximum cost, we'd use the same method. We'd have the feasible region, and then we'd pick fixed costs and basically slide those like lines, making the cost more greater and greater, and basically seeing which intersection point they're approaching.